Okay, so the normal approximation to the binomial distribution. Last class, we learned how to find probabilities involving the normal distribution. Okay, that's where you do a z transformation, and then you learned how to find areas under the z distribution. You look up things in the table. You had to apply some formula, some stuff. But we got really good at doing normal distribution problems. Okay, last class, and that's what you had the quiz on today. But well, the lecture for today, section 7.4, is not, these problems are not normal distribution problems. They're binomial distribution problems. Binomial distribution is what you learned in section 6.2. Okay. So look, chapter 6 is about discrete random variables. Chapter 7 is about continuous random variables. Today, every problem we're going to do is a section 6.2 problem. It's a binomial distribution problem, which means it's a discrete random variable problem. Even though every problem is binomial, it turns out that for some situations, you can treat it like it's a normal distribution problem, which is wonderful because when we did binomial, usually students don't do well on the binomial one. It's a tough section, and students usually do much better on the normal distribution section. So please understand, let me say it again. Every problem in this section is a binomial distribution problem, section 6.2 problem. That's the one with successes and failures and all that stuff. But when we do the problem, we're not going to treat it like a binomial problem. We're going to treat it like a normal distribution problem. Now, why do we care about that? So the main reason is when we did binomial distribution problems, the questions I would ask you would have like maybe 2 terms in it, maybe 3 terms, not that many terms. But if I give you a problem that has a lot of terms, like maybe the problem has like 70 terms, you don't want to calculate 70 numbers and add them up and get the answer. That would take forever. So this is one benefit of having this section, is that you could take a problem that would normally in section 6.2 have 70 terms and just do one quick z transformation kind of thing and get the answer, and you get the answer much faster. So you get the answer much faster this way. But the bad thing, so that's the good thing about this section. The bad thing is it's an approximation. You're not going to get the right answer. You're going to get a close to right answer, and hopefully it's going to be very close to the right answer, but you're not going to get the exact answer. So if you wanted the exact answer, you'd have to add like all 70 terms, for example. So the main benefit of this section is that when there's a lot of terms, you can answer the question really fast instead of take a long time to do it. But the bad news, you're going to get an approximation. It's not going to be the exact answer. But if all you need is an approximation, you don't want the exact answer, then this is the way to go. Okay, now as far as the exam goes, like I understand this section is not that easy, so we'll go through it slow. Hopefully everything will make sense. Please stop me if you have any questions along the way. But on the exam, how are you going to know it's this kind of problem? I'm going to make it crystal clear, okay? It's going to say, use the normal approximation to the binomial to do this question. Okay, it'll say something like that. If it doesn't say that, don't do what I'm going to teach you in this section. Okay, the online homework might not say that, but the online homework will say section 7.4, and you'll know that it's all these kind of problems. But I'll be crystal clear on the exam. For this problem, use the normal approximation to the binomial or something close to that. Okay, so that you know that you do the stuff you're going to do in this section. In other words, on the exam, you'll probably have 2 binomial problems. One of them is I'm testing you on section 6.2, and the other one I'm testing you on section 7.4. How do you know which one use the binomial formulas from 6.2? How do you know when to use the 7.4 one? I will say this, normal approximation to binomial. Okay. All right. So, but let's learn how to do this stuff. So we got story. So let me remind you about what a binomial variable is first, because every problem in this section is binomial. So there's basically 4 ingredients you had to look for a binomial problem. What does it say here? You're in a binomial situation if the first thing the problem has to say is you're going to do something a bunch of times. Like you're going to flip a coin and you're going to repeat it 80 times. So you're going to flip a coin 80 times. Or you're going to draw a card out of a deck of cards 30 times. You're going to do something and you're going to repeat it over and over again. Okay? That's the very first thing, every binomial problem. You're going to do this and you're going to repeat it over and over again. And they're going to tell you how many times you're going to repeat it, and that's what we call n. So little n is how many times you're doing whatever you're doing. And even though we're going to do something a bunch of times, every single time you do what you're doing, the outcome is going to be either a success or a failure. Again, it's every single time you do what you're doing, the result is going to land into one of two groups, one of two categories, and success or failure are what we call the two categories. Success is what the question asks you about, and failure is everything else. So like when you're flipping a coin, if I say you can flip a coin 80 times, so the probability it lands on heads 32 times. Since I asked about landing on heads is a success. That means landing on tails is a failure. If I said you're going to draw a card out of a deck of cards 30 times, what's the probability? 7 of them are hearts. Because I mentioned hearts, hearts are a success. So every single time you draw a heart, you've got a success. If you draw a card and it's not a heart, then it's not a success. It's a failure. Okay, I didn't write independence here for some reason. So that would have been, we called this number 4 last time. Number 3 would have been independence. Let me just squeeze that in there. In other words, every draw has to be independent of every other draw, meaning if you're drawing out of a bag or a deck of cards, something, you got to draw with replacement. There has to be independence. What did I write here? Independence. Interesting. Sorry about that. Independence. So it has to be independence in the problem. And the fourth thing, the problem has to ask you to find the probability of getting a certain number of successes. What's the probability of getting this many successes? What's the probability of getting 18 hearts if you draw a card 50 times? What's the probability coin lands on heads 12 times if you flip it 32 times? That kind of thing. They're going to say, what's the probability of getting this many successes? And little x will stand for how many successes they asked you for. So if you see those 4 ingredients in the problem, that's a binomial problem. Now, you're not going to write any of these 4 things down. You're going to go through those things in your head just so you could say, hey, now that I went through these 4 things, I know for sure it's binomial. Okay, that's the first thing. So that's how you recognize you're in a binomial situation. Then whenever you're doing a binomial problem, so even today, because every problem is binomial, you have to write down 7 things. There's 7 things I'm looking for. First thing you're going to do is you're going to write down the word binomial. Then you're going to write down these 4 things. You're going to write what a success is in words, what a failure is in words, what little p is, and what little q is. Little p stands for the probability of success. Little q stands for the probability of failure. And when you're figuring out these 4 things, even though the problem says you're going to do something a bunch of times, pretend you're doing it once. So if the problem says you're about to draw a card out of a deck of cards 50 times, pretend you're drawing once. When you draw 1 card, what's a success? If it's a heart, for example. What's a failure if it's not a heart? What's little p? The probability of getting a heart when you draw once, which is like 13 out of 52 kind of thing. Little q, that's a probability of not getting a heart when you draw once. So to figure out these 4 things, you imagine doing whatever you're doing once, even though that's not how many times you're doing it. They're going to tell you in the problem how many times you're doing it. So those are 5 things, okay? So binomial and those 4 circled things there. And then you're going to write down little n and capital X. Little n is how many times you're doing whatever you're doing. And capital X is you're just writing what the random variable is. It's always the total number of successes, but don't write the word success. Write what a success is in your problem, like the total number of hearts drawn, or the total number of times a coin lands on heads, or whatever it is in the problem. So you're going to write down those 7 things. Okay. And these are the 4 formulas I gave you back in section 6.2, the binomial formulas. This is what you use if you're treating it like a binomial distribution problem. But today we're not going to use this, okay? Because again, most of the problems, there's going to be so many terms that you'd have to use this formula so many times that we have a better way to do it. We have a normal approximation way to do it. So instead of doing 70 things and adding them up, we could just do 1 thing, okay? But the problem is we get an approximation. So if on the exam, it's a section 6.2 problem, if it's a binomial problem and I don't want you to do the stuff in this section, then this would be the formula you use to find probabilities. But we're not going to use this in this section. But I am going to need these. Those are the formulas for the expected value, standard deviation, and variance. I guess I don't need the variance technically, but we'll need the expected value and the standard deviation formula. Because when you're doing normal distribution problems, let me say this one more time. Every problem in this section is binomial, but we're going to treat it like it's normal. It's not normal. We're going to treat it like it's normal. Well, how do you do problems when they're normal? You do a z transformation. You have to minus mu divide by sigma. What mu am I going to use? This one. What sigma am I going to use? This one. You can use the mu and sigma from the binomial section because every problem in this section is binomial. Okay, so these 2 circled ones we're going to need. All right. Suppose x is binomial. As long as this condition is true, then the distribution is approximately normal. Okay, before I continue, you can't always use the normal distribution to approximate a binomial distribution variable. Okay, so there's a condition you have to check. I'm going to want you to check it. I'm going to show you exactly everything you need to do, but we're only going to do one example. Okay, today it's going to be a long example. We're only going to do one. So this condition has to be true in order for you to pretend it's normal. So remember, x is binomial. Okay, x is binomial. Every problem in this section is binomial. But as long as NPQ is greater than 10, what does this mean? This means you have to multiply n times p times q, which is, those are 3 of the 7 things you wrote down at the beginning. Multiply them together. They have to be greater than or equal to 10. If the answer to that is greater than or equal to 10, then we can pretend x is normal. It's not normal. We're going to pretend it is. It's approximately normal. So if you pretend it's normal and then calculate the probability that's asked of you, you'll get a very close answer. Okay, so one more time. If x is binomial, but this condition NPQ greater than 10 is true, then x is approximately normal, and the mean is going to be mu, which is n times p, sigma is squared of NPQ. Again, where did these come from? These came from the binomial section. Okay. All right, why do we care? I mentioned this already, but let me go through it again. If the number of terms in a binomial is large, the binomial probability formula, the one with the NCX, all that stuff, it's going to make it a long problem, okay? Which you could do it, it's just going to be a long problem. So the good news is if we use the normal distribution, we're going to get the answer much faster. That's the good news. We can do the problems very fast. The bad news is it's an approximation, so it won't give you the exact answer, but it'll be reasonably close to the exact answer. All right. I guess I should say one other thing. Normal distributions are kind of the most important distribution there is, okay? Everything is close to normal, okay, under certain conditions. So I guess this is one illustration of that. So the binomial variable under this condition is approximately normal. We'll see some other ones in chapter 8 and so on. So basically, when things get real complicated, it turns out that the variable, even if it's not normal, it's close to normal. That's kind of the idea. Okay, now, the continuity correction. This is the part that's going to get a little weird. Okay, what's going to happen is they're going to give you some numbers in the problem. The numbers they give you in the problem are not going to be the numbers you're going to use in the problem. Like when you're doing your Z transformation or whatever, you're not going to use the number that's given in the problem. You have to change the number that's given. So there's multiple ways I can teach this. So I just picked a way, and I'm going to teach it this way. If you don't understand it, so make sure you understand it, because if you don't understand it, you know, there's so many different ways it could be explained. But if you, like, let's say you read the book and they say it a different way, now you're going to be like, wait a minute, he said this, book said this. Or if you talk to another person from another class, another professor, they might say something different than both of those. So I got to pick one of the ways and teach it to you. So I picked one way. Let's make sure we understand this way. And again, if you have any questions, let me know. But the number that's given in the problem will not be the number you're going to use. What you're going to have to do is you have to change the number. Sometimes you're going to change the number one time. Sometimes you're going to change the number twice. Once you figure out what the correct number is to use, it becomes a problem like last section. You do Z transformation and you're done, okay? But you have to first figure out what the number is that you have to use. Okay, so let's see what it says here. Going from the binomial to normal alone will not give correct answers because binomial is discrete and normal is continuous. Binomial is a chapter 6 variable, normal is continuous, chapter 7. We're going from discrete, because everything is binomial today, so everything is discrete. We're going to treat it like it's continuous, like it's normal, like it's continuous. You can't just do that. You're not going to get that close answer. So we have to adjust the number. To fix the problem, you have to add or subtract 0.5 from the number in the question. The number of numbers in the question. Actually, we're going to have to do two things. But this changing the number by 0.5 is called the continuity correction. But let me be a little more clear. So there's going to be two things we're going to do. The number is going to change twice. Well, sometimes it'll change once, sometimes it'll change twice. The continuity correction one will change the number by 0.5. The other thing that I'm going to show you how to do will change the number by 1. So the first step will be take your number and decide if you should change it by 1 or not. And then after you've changed it by 1, then you'll do the continuity correction and change it by 0.5, and then you could do the problem. Okay, so a few things to tell you here. Let me see, do I want to look at this? Let's get rid of this and let's just look up here. Okay, so first thing you're gonna do is you're gonna write down the problem. Let's say I say you're gonna draw 80 cards out of a deck of cards. What's the probability that you get less than or equal to 30 hearts? Let's say that's the question. If it's a less than or equal to, see the symbol and then this symbol, this one is the important one. I like that one. We like less than or equal to. We don't like less than. We like this one. We don't like this one. Okay, so if it's a less than or equal to in the problem, you don't need to do the first adjustment. So I call it 2 adjustments. The first adjustment to the number you don't need to make. If that is the symbol, or if this is the symbol, greater than or equal to, you can skip the first adjustment. In other words, you don't have to change the number by 1. But if it's this symbol, if it's less than or greater than, with no line on the bottom, there's no line, then you have to do a first adjustment. You'll have to change the number by 1. Okay. Now let me mention something else. Last class, I told you that if it's this symbol or this symbol, it doesn't matter. And that's true. If it's a continuous random variable, but our variable today is not continuous. Our variable is binomial, which is discrete. So in a chapter 6 problem, then these things do make a difference. Okay. I know we're going to treat it like it's normal, but still it's binomial. So those symbols will give us different answers. So what symbols do we like? We like less than or equal to. We like greater than or equal to. We don't like less than. We don't like greater than. So if it's a less than or a greater than, I'm going to show you how to change it to a less than or equal to or a greater than or equal to. And when you do that, you're going to add or subtract 1 from the number, and I'll show you how that's going to go. So that's going to be a little bit complicated, but we'll have to figure that out. Okay, so let's make sure we're clear. Less than, we don't like. Greater than, we don't like. Less than or equal to, we do like. Greater than or equal to, we do like. So if the problem has a less than or equal to in it, or a greater than or equal to in it, when you start the problem, you don't have to change the number by 1. You don't have to make this first adjustment. But if the problem has a less than or a greater than, then we're going to have to change the number so that it has a less than or equal to or greater than or equal to in the problem. Okay, so that will be the first adjustment. And what will happen when you go from less than or greater than to less than or equal to or greater than or equal to is the number will change by 1. Okay. After you've done that, then you're going to do the continuity correction. And when you do the continuity correction, the number will change by 0.5. Let me try to explain a little bit why the number will change by 0.5. Okay, let's say, so let's say you're going to roll the die once. And ask you to find the probability that you get a number between 3 and 5. Let's put less than or equal to because we like that. So you can answer this question really easily because when you roll a die, there's 6 outcomes total. And I'm saying we'll probably get a number between 3 and 5. So 3 or 4 or 5. So how many outcomes is that? There's 3 outcomes there, right? 3 or 4 or 5. So probably is 3 out of 6. And I could draw a picture of this. This is a histogram. When you roll a die, normally you would draw a picture that would look something like this. The probability of rolling a 1 is 1 out of 6. And let me put these numbers. So the numbers on the bottom are all the different numbers you can roll when you roll a die. Okay. The probability distribution in a chapter 6 or a discrete random variable would be a histogram. Would be a bunch of rectangles. All the rectangles would have the same height. So like this one I'm drawing right here, this third one, the bottom number 3 is saying the probability of getting a 3. If you want to find the probability of getting a 3, you go look at the height of the rectangle, and the height is 1 out of 6. They all have height 1 out of 6 because they're probably getting any number on the die is 1 out of 6. If we get a histogram like this, sorry, these rectangles are not looking that great. Let's draw them better. Okay. I don't know, a little bit better anyway. Okay. And then to find the probability of getting a 3, 4, or 5, there's a 3, there's a 4 rectangle, there's the 5 rectangle. You just add 1 out of 6, right? 1 out of 6, 1 out of 6, 1 out of 6. You get 3 out of 6. Okay. All right, but let's take a look at the numbers on the bottom. The number 1, I'm writing it like in the middle of the rectangle, okay? But the rectangle is starting here and ending here. The second rectangle is starting there, ending there, and then so on. These lines I'm putting, these tick marks I'm putting are not at 1, 2, 3, 4, 5, 6. If you were going to treat this like a continuous random variable, what that means is you would treat like the top of the rectangles as like a curve. Okay, and then so we have like this horizontal line, like a uniform distribution. And then if I said find the probability of getting a number between 3 and 5 in a continuous random variable kind of problem, what you would do is you would start at the number 3, which is here. You would go up to the curve. You start at the number 5, which is here, and go up to the curve, and you would shade between. Okay, and this blue area should be the answer, but that blue area does not make sense to be the answer because take a look at it carefully. I know it's getting a little bit ugly, but let me go ahead and emphasize the rectangles in there. Here's the number 4 rectangle, which is completely in the blue region. The number 3 rectangle, let me change the color. You see how only half of it is shaded? Okay, and same thing with the 5, half of it's shaded. So if you treat it like a continuous random variable, then the shading is not supposed to start at 3 and end at 5. It's supposed to start here and end here. Okay. Well, tell me this number right here. What number is that? From the picture, can you guys tell me?
2.5.
Yeah, it's 2.5. And what's the other one? Sorry?
5.5.
5.5, right. So that's the idea. If you would have, so if you're trying to find the probability of getting a number between 3 and 5, but you treat it like a continuous random variable, then you should start the shading at 2.5 and end at 5.5. Then when you shade the whole thing, you've now taken all 3 of those rectangles that you were supposed to count, and they're all counted in there. So that's the idea, that if you go from discrete to continuous, the numbers have to change by 0.5 to make sure all the rectangles you wanted to take into account are accounted for. Okay, so that's a little bit of a story. If it didn't make too much sense, don't worry that much about it, but I just wanted to give you an idea of why the numbers change by 0.5. So if this was the question, you would change it to probability of getting a number between 2.5 and 5.5, and then you would do the problem. I will still show you how to figure out what the numbers are. This explanation was just so you can understand why 0.5. Because discrete is a bunch of rectangles, continuous is area under the curve, but then you got to move the numbers so you kind of get all the, you count the entire rectangles kind of thing. Okay, so here's what we're going to do. In every problem in this section, you're going to first write down the notation. Make sure you get it right, because you're going to need to know, is it a less than, is it greater than, is it a less than or equal to, is it a greater than or equal to, which of those symbols is it? You got to make sure you get it right. Then, if the symbol is a less than or a greater than, we're going to have to make an adjustment to the number that's in the problem so that we can rewrite the notation with the less than or equal to or greater than or equal to. When we do that, the number will change by 1. We're either going to add or subtract 1. Again, I'll explain when do you add 1, when do you subtract 1, we'll talk about it. So again, if the problem already has this less than or equal to or greater than or equal to in it, you can skip this first adjustment. But if it has a less than or a greater than, you're going to have to adjust the number. It's going to change by 1 so that we have these symbols. We like less than or equal to, we like greater than or equal to, we don't like these symbols. After you do that, then you can do the continuity correction. The continuity correction, we're going to have to add or subtract 0.5 from the number that we have, whichever way makes the area bigger. Again, we'll talk more about it. But last thing to tell you is this step 1, sometimes we skip it. Okay, if these are the symbols that are used, we could skip that. But step 2, the continuity correction, you always have to do it. Every problem you have to do the second adjustment. The first adjustment, you may or may not have to do it. It depends on the problem. All right. And on that note, I've told you everything there is to tell you, but we do have to see it in action when we do a problem. So this is the problem we're going to do today. So let's go ahead and see what it says. According to American Airlines, their flights are on time 90% of the time. If 150 American airline flights are randomly selected, let's go to part B. We'll do part A at the end. Part B, what's the probability at least 130 flights are on time? Okay, so I'm going to go through some stuff in our heads. Let's first see that this is binomial. There's 4 things you're supposed to check, right? You're supposed to be repeating something a bunch of times. When they say 150 flights, let's say 150 flights are randomly selected, I want you to think of it as we're going to randomly select a flight, and then we're going to repeat that 150 times total. Remember, every binomial problem, you got to be repeating something a bunch of times. In this case, we're randomly selecting a flight. So randomly select a flight, and we'll do that 150 different times. Okay, that's the first ingredient for binomial. The second one, the second ingredient thing we look for to see if it's binomial or not is success and failure. What's a success? What's a failure? Let's read the question. The question says, what's probably at least 130 flights are on time? So if the flight is on time, that's what they're asking us about. So if the flight is on time, that's a success. So when you look at a single flight, if it was on time, it was a success. If it's not on time, it's a failure. Even if, and so that's for every single flight. We're going to do this 150 times. So we're going to get 150 different success and failures, right? So success is if the flight's on time, failures if the flight is not on time. Third ingredient we look for is independence. They don't mention independence, and I mentioned this to you that in section 6.2 and then now in section 7.4, sometimes they won't mention independence and you're going to have to assume it anyway. Okay, so we're just going to assume it. When they say 150 flights are random selected, imagine all American airline flights are put into a hat kind of thing. Like you write down all the information of the flight on an index card for every flight ever, all put in a bag or a hat. And you're going to select from the hat, you're going to put, and after you select your first flight, you put it back, mix them up, and do it again. So you're going to select with replacement. They don't say it, but again, they should say it. But if they don't, we're going to be assuming it in section 6.2 and in section 7.4. And the last thing is the problem has to ask you to find the probability of getting a certain number of successes. That's what it asks, probability of getting 130 successes, or at least 130 successes. So that's a binomial problem. So you just go through those ingredients in your head. You don't write anything down for that. Then you're supposed to write down 7 things. So let's go over here. So before we even look at part A we're going to skip for now, but over here I left room for us to write down the 7 things you're supposed to write down. Actually, there's more things you have to write down than that. So in section 7.4, here's what you're going to write. First, we're going to write down the 7 things you need to write down anytime it's a binomial problem. You're going to write down the word binomial. I'm going to put in a box. I always put in a box. I don't know why. You don't have to do that. Anyway, binomial. Then you're going to write down n. Okay, someone tell me what n is. What number is it in this problem?
150.
It's 150. It's how many times you're doing whatever you're doing total. And in this case, we're selecting a flight 150 times. Then you're going to write down what a success is in words. And again, to figure out what a success is, think about selecting one flight. I know we're selecting 150 flights. Select one flight. It's a success if it's what?
If the flight's on time.
Flight is on time. Okay, the word the means one, so I don't need to write any more about one. But it'd be nice to emphasize that's for any single flight. Okay, so any flight you select, if it's on time, it's a success. If it's not, it's a failure. So failure. If the, because it sounds a little confusing. What do you mean the? We're selecting 150 flights. Every single flight, if that flight is on time. So if, and the failure is if the flight is not on time. Then you write down little p, which is the probability of success. In this problem, they give it to you. They say it's 90% chance that a flight will be on time. I'm going to write as a decimal, 0.90. And then little q is probability of failure. To get probability of failure, remember that these two numbers have to add to 1. So this is 0.10 or 10%. Well, if it's 90% chance of being on time, 10% chance of not being on time. So you write those, that's 6 of the 7 things, and then you're going to write down what x stands for. X is always the total number of successes, total number. I'm not going to write the word success, I'm going to write what a success is. A success is if the flight's on time. So it's the total number of on-time flights among the 150 selected flights. So basically what we're going to do is we're going to select 150 flights, and then we're going to count how many of them are on time. Okay, those are the 7 things you're supposed to write down anytime you're doing a binomial problem. And if this was section 6.2 problem, you can now go and do the problems. But because it's section 7.4, there's more things I need you to write. Next thing you're going to do is you're going to write down the condition. Please make sure you do this because I'm checking this when I grade. You need to check the condition NPQ greater than or equal to 10. It will always be greater than or equal to 10 because if it's not, you can't do what we're going to do in this section. But I want you to check it. What's N? It's here, 150. And we put letters next to each other, it means multiply. So you got to do 150 times P, which is 0.90, times Q, which is 0.10. And you calculate this on the calculator. Let me get my calculator out. I'm getting 13.5, which is definitely greater than or equal to 10. So the condition is true. Because the condition is true, so X is approximately normal. X is binomial, okay? But because this condition is true, I can treat it like it's normal. That's what I've written here. All right, last thing to write down then, again, if it's normal, I need to know the mu and sigma because we're going to do z transformations. The formula for mu is n times p. This is the formula for the expected value for a binomial given back in section 6.2. N is 150, p is 0.90, is 135. And then sigma is square root of NPQ. So 150 times 0.90 times 0.10 square root of this. Now, if you type this in the calculator, it's going to be an ugly answer. When that happens, you do not want to round it, okay? Because you're gonna end up looking up wrong numbers in the table later on. So this is what I suggest you do. If you can calculate the answer, but if the answer is a long decimal, this is what I suggest you do. Just multiply the inside numbers, which we did back over here, and then just write square root of 13.5. Just leave it like that, okay? If you do square root of 13.5 on the calculator, it's this real long number, but if you round it, you're gonna make mistakes because you're gonna look up wrong numbers. So my suggestion is don't round any number until you absolutely have to. So just leave it like this. Nothing is rounded here. This is exactly what sigma is. So leave it like that, and then we'll round when we have to. Okay, please don't forget to write it. These are the kinds of things that I don't remind you on an exam to write. Okay, so if it's a section 6.2 problem, write all this. If it's a section 7.4 problem, write all this and all this before you start any parts of the problem. Okay, and it's useful too, because once it's all there, then when you can go back and look at it and get the information you need for every part of the problem. Okay, we're gonna skip part A, let's go to part B. We'll come back to part A. That'll be the last part we do. Let's look at this one. What is the probability at least 130 flights are on time? Okay. At least, so what does at least 130 mean? It means 130 or bigger. That's what at least 130 means. The notation for that is probability that X, remember X stands for, let me go back a slide or 2 slides. X is the number of on-time flights. I'm asking you, what's the probability the number of on-time flights is at least 130? Finish the notation here. Probability X what?
Greater than or equal to
Keep going.
130.
Greater than the 130. Okay, perfect. All right, so you have to get the notation right. If you wrote greater than instead of greater than 130, it's going to cause problems. If you wrote less than or less than or equal to, it's going to cause problems. You've got to get the notation right. So make sure you know what at least 130 means. At least means that or bigger. That's what at least means. 130, at least 130, 130 or bigger. So it's greater than or equal to 130. Okay, I'm going to write the word binomial up here. Whenever you start the problem, the variable, we're treating it like it's binomial. Now, let me ask you this question. Do I have to make one adjustment to the number or two adjustments to the number?
One.
One, that's right. Okay. The first adjustment you would make, you don't have to make if it's a greater than or equal to, or if it's a less than or equal to. So had that been a greater than or a less than, we'd have to make two separate adjustments to the number. But because that's a greater than or equal to, the first adjustment can be skipped. We're going to go straight to the second adjustment, which is called the continuity correction. I'm writing that above the equal sign, CC for continuity correction. Here's what you do. You're just going to change the number. How do I figure out what number to change it to? Okay. As far as the continuity correction goes, this is how you figure it out. I'm going to draw a picture. You do not have to draw this picture. I do not need to see a picture, but if you want to draw it and it helps you, great. But so I'm going to draw it real quick, then I'll erase it. But I'm imagining a normal distribution. The truth is 135 is right here because that's the mean, but I don't really care. But anyway, 130 is less than that, so 130 is over here. Greater than or equal to 130 means go up to the curve and shade to the right. That's what greater than or equal to means. The way I'm teaching you how to do the problem, again, there's multiple ways of teaching it to you. The way I'm teaching it, this area that I've shaded will always be too small. You need to make it bigger by moving this line. Okay? So we have to shade to the right of the line. The area I've just shaded right now is too small. To get more area in there, which way would I have to move the line? Do I need to move the line to the left or move the line to the right?
To the left.
To the left, you're right. If you move this line a little bit to the left and put it here, then shade to the right, you're going to still shade all this area again, but you're going to get this extra little bit of area here. You have to make the area, you always have to make it bigger. Again, if it sounds weird, it's because that's the way I'm teaching it. There's different ways of teaching it. You have to move the line to make the area bigger. So then the line had to move to the left. So this number is going to be less than 130. What number is it going to be?
129.5.
That's right, 129.5, because you have to change it by 0.5 when you're doing the continuity correction. So how do you know if it goes down or goes up? Draw a picture. Whatever the area is, make it bigger. Okay, so it totally depends on the problem. If it's area to the right, you need to move that thing to the... I don't want to give you a whole bunch of things to memorize. You're going to forget them all. I could say, okay, when it's a greater than, make the number smaller. When it's a less than, make the number bigger. They go, oh, wait, which one do you do? Make the area bigger always. Okay, the area is always too small. So the number is going to be 129.5. Okay. And now that once you're done with the continuity correction, now you could treat the variable like it's normal. And now we can go ahead and Z transformation this thing and get it done. So it's all about, the hardest part, if you ask me, is getting the correct number to use. The number in the problem was 130. What's the number we're going to use? 129.5. And now we'll do the problem. Any questions so far? Okay, let's erase this picture again. I do not need to see the picture. But again, if drawing the picture is going to help you not make a mistake, draw it. I won't grade it. Just draw it, get the right number to use. Okay, now that it's normal, we're going to do what we did last class, Z transformation. When you do Z transformation, you copy down the P symbol, you copy down the parentheses symbols, you copy down the greater than or equal to, And in each spot, you take what was originally there. In this case here, we have an x, and you minus mu, and you divide the whole thing by sigma. In this spot, same thing. What was originally there was 129.5. Copy it down. Minus mu, divide the whole thing by sigma. The part that has the x minus mu over sigma, that's z. The other part, 129.5 minus, all right, what was mu? It was on the previous slide. Mu was 135. Let me go back. Mu 135. Sigma squared root of 13.5. 135 square root of 13.5. All right, now I'm going to calculate this number. So let's see, 129.5 minus 135 divided by square root 13.5. Now this, I get some long number here, but here's the deal. I told you that when you're doing a z problem, the number in the parentheses, you must round to 2 digits after the decimal. That's why I don't want you to round at all until you get there, okay? Because if you do any other rounding, then when you get here, you might end up getting the wrong number to put here. So that's why I don't calculate square root of 13.5 and round it. But now when you calculate this whole answer for this, go ahead and round it. I'm getting negative 1.496, whatever. When you round that to 2 numbers after the decimal, it's negative 1.50. Okay, it was negative 1.496910398. You're supposed to round to this spot. Because this number here is bigger than 5, you have to add 1 to this 9. It becomes 0. Add there, 5. You get negative 1.50. Okay. Any questions on that much? Okay. Now, what's the z greater than problem? How do you do a probability z greater than something? You have to use a formula. The formula is 1 minus probability z less than the number. And then the less than, you can look that up in the table. So it's a negative number. Look it up in the negative side of the z table. We're looking up negative 1.50. Here it is, negative 1.50. 0.0668. And the answer to this problem is 0.9332. All right. That's your first example for the types of problems we're doing today. Any questions? All right. Now, this is not the right answer. This is it's an approximation. But this is the work you're going to do, and this is the answer you're going to give me. But how many terms is this? It says at least 130 flights are on time. If I was going to use the binomial variable, the binomial formula, how many terms would it be? Well, at least 130 flights means 130 or 131 or 132 or 133, all the way up to 150, because you can't have more than 150 on-time flights if you're only looking at 150 flights. So that'd be 21 terms. So if you use the binomial formula, instead of this couple of steps here, you'd have to calculate 21 different things and then add them up. And if you did that, you would get the exact answer. This is not the exact answer. This is an approximation to the exact answer. So this number here is the exact answer to part B. So I calculated the exact answer using Excel. I added the 21 terms. It actually is 0.9279. Just in case you're wondering, the exact answer is 0.9279. Our answer is 0.93 something. So the exact answer was 0.92 something, and the approximation answer is 0.93 something. So you're seeing it's super close to the exact answer. Okay, we've got to do a million more of these, but any questions on part B?
No questions.
Okay, let's go and look at part C. What is the probability that more than 130 flights are on time? Okay, let's write down the notation first. Someone tell me the notation. Probability more than 130 flights are on time. Let's get the notation. Let's make sure we get it right. So it's probability of what?
Of x greater than 130?
Right. The last problem was greater than or equal to. At least means 130 or more, but more than means greater than, no equal to here. Okay, so you write down the notation, make sure you got it right. Then I'm going to write down the word binomial here. For right now, we're treating it like it's binomial. But we're going to change the number. It's going to eventually be normal, and then we'll do z transformation. Okay. So let me ask you now, for this problem, am I going to change the number once, or am I going to change the number more than once? So once or twice?
Twice.
Twice. Why? Because the first adjustment has to be made because I need the symbol to be greater than or equal to. So look what I wrote there. I wrote everything except for the number. Now I got to figure out what the number is. Okay. This part, so how do we explain this part? Remember what's happening here. We're looking at 150 flights, and we're going to count how many are on time. If you look at 150 flights and count how many are on time, how many could be on time? You could have 0 flights on time, 1 flight on time, 2 flights on time, 3 flights on time, up until what? What's the biggest value x could be?
150.
150. And let me put some other numbers in here. So you're just going to count how many are on time, and you're going to get a whole number for sure. You can't get like 2.7 flights, right? So either 5 flights or 8 flights or whatever are on time. It'll be 149. Let me get the number 130 in here because 130 is mentioned in the question. I'll put one number bigger, one number smaller. Okay. What is greater? So which of these numbers are greater than 130? Which ones?
131.
Is one, so 129 is not greater than 130, right? So
No.
this one is not, this one is not, this one is, right? And all of these are. So when they say greater than 130, they're talking about these numbers. Okay, so greater than 130 is the same thing as greater than or equal to which number?
131.
131. Okay, so the first thing to understand is that if saying that x is greater than 130 and saying x is greater than or equal to 131, you're saying the same thing. Both of those situations are talking about these possible values of x. Now, that wouldn't be true if your variable doesn't have to be a whole number, but binomial variables, they have to be a whole number. Okay. I know this doesn't make sense to be ages, but let's say this is the age of someone, and I'm saying their age is more than 130. It's the same thing as saying their age is 131 or more. You're saying the exact same thing. I want you to notice also that the number changed by 1. Now, if that didn't make sense, we're going to go through a few examples, but now I'm going to give you a second way of seeing it to make sure you get this number right. Because again, you mess that number up, it's going to mess up everything. You know, so let's say you didn't like this picture, but I really want you to understand this picture. But if you, let's say you didn't like this picture, you know this number, when you change from a greater than to greater than or equal to, is either going to be 131 or 129, because this number is going to change by 1. Okay, then you could just ask yourself, is 131 greater than 130? Yes. Is 129 greater than 130? No. So it's got to be the 131. It's got to be one of the numbers we're talking about. It's got to be greater than 130. So it can't be 129 because it's not greater than 130. Okay, so anyway, so the number in our first adjustment, we changed the number from 130 to 131. There's no name for this adjustment, so I'm just going to leave it like that. Any questions on that much? Let me see what the chat is saying. Okay, so no questions? All right, so then we're going to do the continuity correction. This is the second adjustment. This adjustment you have to always do. Whether or not you have to do the first one or not, you have to do the second one. In the second adjustment, the number will change not by 1, but by 0.5. So now I'm going to leave the number blank again. I'm going to draw a picture here. Again, you do not need to draw this picture, but okay, 131. We draw a line at 131. The number we're at, don't draw it at 130, okay? Draw it at the current number we're at, 131. And since it's greater than or equal to, we're supposed to shade to the right. And again, the way I'm showing you how to do this this area will always be too small. We need to make it bigger by moving the 131 line. We have to shade to the right of the line and end up with more area. So where do I have to move the line? To the left or to the right?
To the left.
The left. Because if you move the line a little bit to the left, then shade to the right, you've got this extra bit of area in here you didn't have before, and the rest of it. So you made the area a little bit bigger. Because the line moved to the left, the number is a little bit smaller than 131. So we're going to have to subtract 0.5. That's going to give me 130.5. That is the number we will use to do this problem. After you're done with the continuity correction, I want you to write normal above the parentheses. And now we treat it like a problem from the last section. Okay, any questions so far? All right, sounds good. So now that it's normal, what are we going to do? Z transformation. All right, so anytime it's a normal problem, you do a Z transformation. What you do is you copy down the P symbol, copy down the inequality symbol, copy down the parentheses. In the first spot here, originally there was an X. You copy that down, and then you minus mu and divide by sigma. That's the Z transformation formula. In this second spot over here, originally there was a 130.5. You're going to copy down the 130.5. Then you're going to minus mu and divide the whole thing by sigma. That's the Z transformation formula. When you're done with that, the term that has the X is Z now. The other term, you're just going to plug in the mu and the sigma. The mu was 135. The sigma was square root of 13.5. And now I will calculate that number. All right, let's see. 130.5 minus 135 divided by square root of 13.5. We need negative 1.22. It's negative 1.22474. You have to round to two numbers after the decimal when you're doing a Z problem. So again, that's why I don't round at all until you must round, and you must round here. Any questions so far? Okay, so then when it's a Z greater than problem, you use a formula, 1 minus probably Z less than the number. Someone might tell me, it's greater than or equal to, shouldn't this be less than or less than or equal to? Well, once we're treating it like it's normal, then this bottom symbol, less than or equal to, does not matter anymore because we're treating it like it's continuous. But until we got to this point, the symbol is very important because it's discrete at this point. Once we got to here, it's continuous. So then if it's less than or equal to, greater than or equal to, it doesn't matter. So write either one, it doesn't matter. All right, now probably Z less than negative 1.22. We looked that up in the table. Looking for negative 1.22. All right, negative 1.22. And then you go like this and like this. Looks like it's 0.1112. And if you do 1 minus that, you get 0.8888. That's how you do part C. Real quick, again, let's go ahead and look at the exact answer because I made a whole thing of exact answers. The exact answer for that one is 0.8870. In other words, if you use the binomial formula, that one would have 20 terms. This one would have had 21 terms. This one has 20 terms. The exact answer is 0.887 something, and our answer was 0.8888. So again, not exactly right, but very close answer. Okay. Anyway, here are the exact answers. I'm not going to look at them anymore, but they're here in case you're wondering for later. So when we look at all the other answers, compare them to these answers, okay? And they should be close. If they're not that close, it sucks, but most of the time they're going to be very close because that's the whole point. Normal approximation of the binomial. These are the exact answers using the binomial formula. What we're doing is we're getting approximate answers by treating the variable like it's normal. All right, I'm going to get rid of this file now because we're not going to use this anymore today. But it's there. You can take a picture of it if you want to compare it to your answers later. All right, let's go back to this stuff. Okay, let's go to part D. Okay. What is the probability that fewer than 125 flights are on time? All right, I need notation. Someone tell me the notation.
Probability of X less than 125.
Yes. And again, it's very important when you get the notation, it's very important you get the notation right. Is it less than, or equal to? So fewer means less. Okay, so it can't be 125, it has to be less. Okay. And again, I'm gonna write down the word binomial. As of right now, I'm treating it like it's binomial. Now, there's two separate adjustments. Do I have to make the first adjustment to the number, yes or no?
Yes.
Yes.
Yes, because I don't want a less than, I want a less than or equal to. So we make this first adjustment. This number will either be 124 or 126. We got to figure out which one it is. This number will change by 1. And again, this is how you figure it out. Here's one way. So here are all the possible values of x. The number of on-time flights can be 0, 1, 2, 3. I'm not going to list them all. It would take forever. Let me get to around 125, 124, 125, 126. I'll keep going to 150. Number of on-time flights is going to be somewhere on this list. What does less than 125 mean? Is this number less than 125?
No.
This one?
No.
These are the numbers that are less than 125. So when it says x is less than 125, they're talking about these numbers, like the probability to get 0 on-time flights or 1 or 2 or 3 up to 124. So less than 125 is the same thing as less than or equal to what?
124.
124. Another way to say it is whatever number you're supposed to put there better be on this list. So 124 is the biggest one, so it's got to be 124. So after you make that first adjustment, which again doesn't have a name, then you're going to do the second adjustment, the continuity correction. That one you always have to do. The first one you don't have to do if it would have been a less than or equal to start with, or a greater than or equal to start with, but it wasn't. It was a less than, so we had to do this first adjustment. For the second adjustment, the number is going to change again. How do you figure out what it changes to? You draw a picture. You don't have to draw the picture, but the number that we're currently at is 124. I'm going to go from there up to the curve, and it says less than or equal to, so that means I'm supposed to shade the left. Less than or equal to. Okay, and again, the way I'm teaching you how to do it, this area I'm shading is always going to be too small. So let's take the line where 124 is, and we have to move it. We're still going to shade to the left, but where should I move the line so that when I shade to the left, I'm shading more area than now? Which way does the line have to move?
To the right.
Move it to the right. So we'll move it to like here somewhere. So that way, if I shade to the left, I get this extra area as well as this area. That means the number is getting bigger because we moved it to the right. What number is it going to be?
124.5.
124.5, that's right. It goes up by 0.5. After you're done with the continuity correction, I'm going to write the word normal above the parentheses, and now we can do the z transformation. So it's all about what number do we eventually use? Even though the problem says 125, we're going to use 124.5. Okay, any questions on those two adjustments to the number? All right, sounds good. And again, you don't have to draw this picture. If you can just visualize it in your head and get the number, that's fine. Otherwise, drawing it is fine. It's up to you. I'm not going to be grading the drawing of a picture for this kind of problem. All right, now that it's normal, what do you do when it's a normal problem? You do a z transformation. So we're going to write down probability, the parentheses symbol, the less than or equal to, and there's two spaces to fill in. In the first space, originally there was an x. You always copy down what was originally there, and then you minus mu and divide the whole thing by sigma. Okay, and then for the second space, same thing. Originally we had 124.5. I'm going to copy what was originally there down. Minus mu, divide the whole thing by sigma. That's a z transformation formula. Then the x term is just z. And for the other term, I will plug in the mu and the sigma. The mu was 135. Sigma was square root of 13.5. That was all the way in the first slide. And then you calculate the number in the parentheses, and you must round it to 2 digits after the decimal. So let's see, 124.5 minus 135 divided by square root 13.5. I'm getting negative 2.8577. When you round that to 2 digits after the decimal, negative 2.86. So don't round until this point, because again, if you do any rounding earlier and you get a different number here, you're going to look up the wrong number in the table. Okay, any questions to this much?
No questions.
Okay, and then it's a z less than number. You look that up in the table to get the answer. So negative 2.86. I'm going to write here negative 2.86. Use the negative side of the z table. Here's negative 2.8. We'll get the last digit from here. So you go like this. And the answer is 0.0021. Okay. Okay, so the new stuff is this. Because after this, all of this is what we learned last class. Okay, just do the z transformation. Okay, so it's like write the notation down and change the number appropriately, make 1 or 2 adjustments so you know which number you're supposed to use. Then just do z transformation like last class. Questions on part D?
No questions.
All right, so let's go to part E. What is the probability that at most 125 flights are on time? At most. Again, we got to get the notation. We got to get it right. At most 125 means 125 or less. That's what that means. Someone tell me the notation.
Probability of X being less or equal than 125.
Right. Okay, again, get the notation right, because the notation is going to let me know how many times I need to change the number. Write down the word binomial here. Because it's a less than or equal to, we don't need to make the first adjustment. Had it been a less than, we would have to make it for the first adjustment. So we can go straight to the continuity correction now. So the number will just change 1 time. And again, how do you figure that out? You draw a picture or visualize a picture, whatever. Let's say here's the number 125. I'm supposed to shade to the left of it because it's a less than. And again, the way I'm showing you how to do this, the area will always be too small. You need to make it bigger by moving the line where 125 is. Which way do I have to move it so that when I shade, I get more area?
To the right?
Yeah, move it to the right. Move it away from the area that you shaded. So now when you shade to the left of the blue line, you get this extra bit of area that you didn't have before, besides the red area. The line had to move to the right, so the number gets bigger by 0.5. So what's the number going to be?
125.5?
125.5. All right. So we put 125.5 there, write the word normal here. And now we will treat the problem like it's a normal distribution problem. Any questions? All right, erasing this. Now we're gonna, once again, just do the z transformation on this. Anytime your variable is normal, or we're treating it like it's normal, your job is to do z transformation. So z transformation. So again, p symbol, parenthesis symbol, and less than or equal to symbol. Here, what am I going to put? I'm going to put what was originally in the spot, x, then minus mu and divide by sigma. For the second space over here, I'm going to put what was originally there, which is 125.5, minus mu, and I'm going to divide by sigma. The term that had the x in it, this whole mess is now z. And for the other part, I'm going to plug in the numbers for mu and sigma. And then I will calculate what's in the parentheses and round to 2 numbers after the decimal. So let's see, 125.5 minus 135 divided by square root 13.5. And I'm getting negative 2.5855 when you round to 2 numbers after the decimal, negative 2.59. Okay, so you do the z transformation, you get negative 2.59. And now it's a z less than problem, so you just look that up in the table, negative 2.59 in the table. Negative 2.5. So there's the answer to that one, 0.0048. Okay, questions on part E. But okay, let's do part F. What's the probability between 125 and 135 flights inclusive or on time? Okay, so it's a between problem. Okay, so how do you write between? Well, you put the smaller number here, you put the variable in the middle, you put the bigger number here. But this means between. This also means between, but they mean slightly different things. When it says inclusive, it means include the n numbers. So you're going to be putting less than or equal to's. Because if you put less than, then x can't be 135. X has to be less than 135. It cannot equal 135. So we're not including this number as possible if you put a less than. Same thing here. If you put a less than there, x has to be bigger than 125. It can't equal 125. But if you say inclusive, because it's the word between, right? When you use the word between in real life, sometimes you mean include the n numbers, sometimes you mean don't include the n numbers. Like if a kid comes up to you and says, I'm between 7 and 9 years old. The kid might mean I'm strictly between. So I'm not 7, I'm not 9, but I'm between. Therefore, I'm just 8. Okay, so between 7 and 9 could mean, I mean 8. Or another person could say, I'm between 7 and 9 years old. And what they mean is, I'm either 7 or 8 or 9. So I'm either between, strictly between, or I could be 7 or 9. I could be one of the n numbers. So to be clear on that, I'm going to use the word inclusive, meaning include the n numbers as possibilities. So you have to include them as possibilities, so we have to put less than or equal to's. Okay. Now, because those are less than or equal to's, we like those, so we don't have to do the first adjustment. So we're just going to go straight to the second adjustment. So the numbers will change by 0.5. Draw a picture. 125 is here, 135 somewhere here. We're supposed to shade in between. This time there's 2 lines. The way I'm teaching it to you, the area I'm shading is too small. You need to move both lines so that when you shade between the new lines, you get more area. So this 125 line is going to move to the left, and the 135 line is going to move to the right, so that when I shade between now, I get this little bit of area and this little bit of area extra on top of the red. So the 125 turns into what number?
124.5.
124.5. And the 135?
135.5.
You just have to look at which way it went. If it went up, you add 0.5. If it went down, you subtract 0.5. The numbers we're going to use when we do the z transformation are these numbers. And now write the word normal. After you do continuity correction, we treat the variable like it's normal. And now we'll do a z transformation. Any questions? So now let's go ahead and do the z transformation. Okay, so to do the z transformation, you copy down the p symbol, the parentheses symbols, and the less than or equal to symbols. And then you do the z transformation on all 3 parts of this, which is you copy what was originally there, and you minus mu, divide the whole thing by sigma. Here, what was originally there was x minus mu divided by sigma. Here, what was originally there, 135.5 minus mu divided the whole thing by sigma. Okay, then the part that had the x in it, so the middle term, is just going to become a z. And for the other ones, you're going to plug in the numbers for mu and sigma. So 124.5 minus 135 over square root of 13.5. 135.5 minus 135 over square root of 13.5. And now both of those numbers will calculate and round to two numbers after the decimal. All right, let's see. This number is negative 2.86. This number is 0.14. Okay, then how do you do a z problem when it's between two numbers? Well, there's a formula. It's probability z less than the number on the right minus probability z less than the number on the left. If you put less than or equal to instead, it doesn't matter. And now we look those up. For this one, we have to look up 0.14 in the table. In the positive table, there's a negative table here, 0.14. 0.14. So you get 0.5557 for that. And then to look up this one, you look it up in the negative side of the z table, negative 2.86, negative 2.86. And you get 0.0021. The exact answer for this is 0.5536. Okay, that's how part F goes. G here. So it says, what is the probability that between 125 and 135 flights exclusive are on time? Okay, first thing is you want to get the notation right. When it says between, you put the smaller number here, you put the variable in the middle, and you put the bigger number here. And usually you either put less thans, or you might put less than or equal tos, or one might be a less than, one might be a less than or equal to. When it says between, you're not really sure, but when it says exclusive, it means the thing we're trying to find the probability of is that we have between 125 and 135 flights on time, but it's not 125 and it's not 135. So you don't put the line here, because if you put the line there, it would mean that part of what we're trying to find the probability of is that we could get exactly 125. It could be 125, but it says exclude them. So you exclude, so you don't put these equal signs here. So it's like you exclude this, so you have to get rid of that and exclude that. So it has to be strictly between 125 and 135. So the notation goes like that. And then I want you to write the word binomial on top of this, because as of right now, this is a binomial random variable. We're treating it like a binomial. Now, that what you do in this section is you adjust the numbers. So the 125 and 135, they may change once or they may change twice. Because these aren't less than or equal to's, we want less than or equal to symbols. We're going to have to do two adjustments. The first adjustment, we will get less than or equal to symbols here, and we're going to have to adjust both numbers. So what does it mean to have between 125 and 135 flights be on time, exclusive? So here are all the different possible numbers of flights you can have on time. Could be 0 flights out of one. We're looking at 150 flights total. We could have 0 flights on time, or 1 or 2 or 3. I'm going to go to around 125. So 124, 125, 126. I don't want to list them all because it would take, you have to list 151 numbers, but I'll list the important ones. 134, 135, 136. Those are numbers around 135, and we're going up to 150. So if it's between 125 and 135, I'm asking you, which of these are between 125 and 135? But you have to exclude the 125 and the 135. So which ones are between? This one is not between. This one's not between 125 and 135. It's equal to 125, but it's not between. These are the ones that are between, and these are not between either. So saying that you have between 125 and 135 flights on time exclusive is the same thing as saying you have between 126 and 134 flights inclusive being on time. Okay, so those are the same thing. That's the first adjustment you make. Okay, then the second adjustment you make is called the continuity correction. Remember, the continuity correction, you always do it. This first adjustment, you if these symbols are in the original problem, you don't have to do the first adjustment, because the first adjustment is to make sure you have less than or equal to's or greater than or equal to's in your problem. We would have them, but so if you have them, you don't have to do that adjustment, but here we didn't have them, so we had to do that first adjustment. Now the second adjustment, the continuity correction, you have to do it all the time. The numbers are going to change again. The idea is you draw a picture, put the number 126 and the numbers 134, the numbers we just obtained, put them on the picture somewhere. Go up to the curve, and we're going to shade between, because it's a between problem. And the way I'm teaching you how to do this area will always be too small. We need to make the area bigger by moving the line. So the line where the 126 is, the line where the 134 is, we have to move the lines so that when I shade between, we get more area. So the way you do that is you take the 126 line, you move it to the left a little bit. So that line would move to there. The 134 line would move a little bit to the right. So that way, if I shade between the blue lines now, instead of between the red lines, you're going to get this extra little bit of area and this extra little bit of area here, as well as the area we already had over here. So if you move the left red line to the left, this number here becomes 125.5. Because remember, it's going to move by half. And because it's smaller, you subtract half. So 126 minus half, 125.5. This one here, you go up half from 134, you get 134.5. And that's the number that goes here. And the number that goes here. After you're done with the continuity correction, you have the right numbers to use. You treat it like it's normal now. And now you'll do a Z transformation. All right, let's erase all this. Okay, so now to do the Z transformation, anytime your variable is normal, you do Z transformation. You copy down the P symbol, the parentheses symbols, the P symbols, the parentheses symbols, and the inequality symbols. And then you have 3 spaces you have to fill in. And what do you fill in those spaces? Well, you look what was originally in the space. So for this space, originally we had this. So you write down what was originally there, 125.5. Then you minus the mu and you divide the whole thing by sigma. And do that for each piece. For the middle piece, there was originally an x there. So you copy down what was originally there, minus mu, divide the whole thing by sigma. Third one, what was originally there, 134.5. Then you minus mu and divide the whole thing by sigma. Now the one that has the x, this mess here, x minus mu over sigma, that whole thing is z. That mess just turned into z. And for the other ones, you're going to go ahead and plug in what mu and sigma are. So 135 for mu, sigma is square root of 13.5. Same thing here, 134.5 minus 135 over square root of 13.5. Then you calculate each of these numbers. And again, when you're calculating a number inside the parentheses for a Z problem, you have to round to 2 numbers after the decimal. So 125.5 minus 135 divided by square root of 13.5. The answer to this, if you round to 2 numbers after the decimal, is negative 2.59. The other one, I'm getting negative 0.14 for that. Okay, again, you have to round to 2 numbers after the decimal. Then when it's a Z between problem, there's a formula you use. The formula is probability Z less than or equal to the number on the right. That's probability Z less than or equal to the number on the left. If you put less than instead of less than or equal to, that's okay too. And these are both less than, so you look them both up in the table. Okay. The first one, we got to look up negative 0.14. Let's go to the table, negative 0.14 we're looking for. Here's negative 0.1, and then the last digit 4 over there. So you go like this, and like that. Looks like these lines meet at 0.4443. That's this number here. Minus. Okay, so to look up the other one, we have to look up negative 2.59. Again, on the negative side of the Z table. So now we're looking for negative 2.59. Okay, so negative 2.5 is here. The last digit is here. And you go like this and like that. And the number is 0.0048. All right, then you subtract those numbers. And the answer is 0.4395. Okay, so that's how you do that one. Again, the new stuff is writing down the notation and adjusting the numbers a couple of times and make sure you get those blue numbers. Once you have those blue numbers, then it's just Z transformation stuff we learned from last class. Also remember, this is not the exact answer. This is an approximation. Okay, so if you wanted the exact answer for this one, you'd have to calculate, it looks like, I think 19 terms and add them up. And when you do that, I showed you earlier on the Excel file what the exact answer is. But anyway, this is not the exact answer, but it's an approximation. All right, so this should be at least very close to the exact answer. Let's go to part H. Part H says, what's the probability that between 125 and 135 flights, including 125, not including 135 flights, are on time? Okay, notation. It says between again, because it says including 125, next to the 125, we're going to have a less than or equal to. There's going to be the little equal to. Since it says not including the 135, next to the 135, we're going to have a less than. We're not going to have this line over here. So between 125 and 135, so 125 less than or equal to, because we want to include 125 as a possibility. We don't want to include the 135, so it's going to be just a less than where the 135 is. That's the notation. Again, I'm going to write the word binomial. All right. Now, do we have to make the first adjustment? Well, we don't have to make it on this number because that symbol we like. But we do have to adjust this number because that symbol we don't like. So the way it's going to work, I need them both to be less than or equal to. So when there's a between problem, they got to both be less than or equal to. So this one will stay the same. This one will change. And again, you have to say, well, what does it mean to be between 125 and 135? Here are all possible numbers of on-time flights. There's some numbers around 125. There's some numbers around 135. 150. But if I say between, so which of the numbers on this list are between 125 and 135, including 125, not including 135? So we're not including 135, and definitely not anything bigger. We are including 125. We're not including one. It's got to be between 125 and 135. We can count the 125. We can't count the 135. So it's that up to that we don't count the 135. So it's these numbers that they're talking about. This is the event, basically. We're finding the probability of getting a number of on-time flights in this box here. And how do we write that with less than or equal to? Well, the number over here has to be on my list. So it's got to be 134. Also remember that this, when you change the number, it's going to change by 1. So it's either going to be 134 or 136, but it can't be 136 because 136 is not on the list of outcomes that I have over here. So it's got to be 134. And now they're both less than or equal to symbols there. So we've made our first adjustment. Only one of the numbers changed because we just had one less than. Now we'll do the continuity correction again. Change the numbers by 0.5 now. So continuity correction. So both numbers will change by 0.5 when you do the continuity correction. Again, picture. Draw a line at 125, a line at 134. And we're going to shade between because the between problem. And again, the way I'm teaching you how to do it, the area you shade will always be too small. We need to make it bigger. The way we make it bigger is we take this line that's on the left side and move it more to the left. We take the other line and move it to the right. And then shade between the new lines. Okay, now we have more area. We have more area because there's this area here we didn't have before, and this area here we didn't have before. So the line moved to there. This number is less than 125, so it's 124.5, because again, it moves by 0.5. And this number over here is bigger than 134, so we're going to add 0.5 to it, 134.5. And the numbers for this problem are 124.5, 134.5. Once you're done with the continuity correction, we treat it like it's normal. Okay, so again, that's the big deal with this section, use the correct numbers. The numbers in the problem were 125 and 135. We're not using those. We're using 124.5 and 134.5. So you make one or two adjustments to the numbers. Once you figured out what the right numbers are to use, then you treat it like it's normal. Now we can go ahead and do Z transformation. All right, so again, the way you do it is you copy down, you copy down the P symbol, you copy down the parentheses symbol, you copy down the less than or equal to's. And in 3 spots, you have to put what was originally there minus mu over sigma. So here, 124.5 minus mu over sigma. In the middle, x minus mu over sigma. Last one, 134.5 minus mu over sigma. Okay, now the one that has the x, this term here, that whole mess is just z now. For the other terms, because you see numbers in the other terms, I'm going to plug in the numbers for mu and sigma, and I'm just going to get one number here. So this is this minus 135 over square root of 13.5. This one is 134.5 minus 135 over square root of 13.5. Okay, now we'll calculate those numbers. Let's see, 124.5 minus 135 divided by the square root of 13.5. I'm getting negative 2.86 here. Okay, looks good. And then the other one is negative 0.14. Okay, and once again, it's a Z problem now. So you're going to use, when it says between problem, you're going to write probably Z less than or equal to the one on the right, minus probability Z less than or equal to the one on the left. Okay, and then you look them both up in the table because they're less than. So for this one here, you're going to look up negative 0.14, which I think we already did, but let's do it again. Negative 0.14. There's negative 0.1, the last digit 4. Looks like we have 0.4443 for that one. And then negative 2.86. Put that one up in the table. We have negative 2.86. Okay, negative 2.8 is there. The last digit 6 is there. You get 0.0021 for that. And you subtract those, you get 0.4422. And that's how that one goes. That's part H. Okay, and then we can go now to part A. Part A said, what's the probability exactly 130 flights are on time? So everything else we did, you know, when you do normal distribution problems, there's really 3 kinds of problems: less thans, greater thans, and betweens, right? So that's what we did. We saw a couple of examples of each of those. But now this one's a little different. This is just exactly one number, exactly 130 flights are on time. The notation for this is probability x equals. Some of you might think, oh, the answer is 0. No, it's not. It would be 0 if we're treating it like it's normal, but it's not normal. Remember, it's binomial. That's part of the reason I'm having you write binomial here. So the answer is not 0. X is not a continuous random variable. It's a binomial random variable. I know we're treating it like it's normal, but when you treat it like it's normal, you have to change the numbers. Okay, so I haven't changed the numbers yet. So for right now, it's binomial. And you could use the binomial formula, the one that goes, you know, probability x equal little x equals NCX, p to the x, q to the n minus x. And it would be very simple because it's just one number here. Okay, so the use of this section is when you're supposed to use this formula like, you know, 30 times or something, and you don't want to do that, then you can do what we're doing in this section to get the answer much faster, but you get an approximation. For this problem, you could just use this formula and get the exact answer. I showed you already what it was in the Excel file. Just go back and look at part A there. But what I'm going to show you now is that even if it's just one number, you can still use the stuff in this section to figure out this probability. Here's how it's going to work. You don't need to do the first adjustment because it says equals right here. okay? We like equals, basically, just like we like less than or equal to, we like greater than or equal to, so we like equals. So you don't do the first adjustment, you go straight to the continuity correction. Okay, the way it works like this is, you know how we've done those between problems, you know, and you have like two lines and you shade between, and this one moves that way and this one moves that way kind of thing. Well, when you have just one number, imagine it's two lines, but they're both at 130. Okay, and we're using to move one of the lines to the left and the other line to the right. So think of two lines right, both at 130. You move one of them to the left and one of them to the right, and then you're going to shade between. Okay, so what's this number then? This number is going to be less than 130, and you're going to have to go down by half, so it's going to be 129.5. This number is going to be bigger than 130, and again, you're going to go up by 0.5. This is going to be 130.5. So what basically an equal problem changes into a between problem, becomes 129.5, less than or equal to x, less than or equal to 130.5. If you write less than instead of less than or equal to, at this point it's okay, because after you've done the continuity correction, we treat it like it's normal. Okay, so we're not treating this like it's normal, because then the answer would be 0. But when you adjust the numbers, go 0.5 on either side of 130, now we treat it like it's normal. And now what do you do in such a problem? You do a z transformation. Let me do the z transformation here. So each one of these pieces, you're going to copy down what was originally there, and then minus mu and divide by sigma. So it's going to be 129.5 minus mu divided by sigma. Okay, middle term is going to be x minus mu divided by sigma. Last term, 130.5 minus mu divided by sigma. Again, the middle term, the one that has the x in it, will become z. And for the other ones, I will plug in the numbers for mu and sigma. This is 129.5 minus 135 over square root of 13.5. One is z. This one is 130.5 minus 135 over square root of 13.5. Now remember, inside the parentheses of a z problem, you have to round to two numbers after the decimal. So let me go ahead and get this on the calculator. 129.5 minus 135 divided by the square root of 13.5. I'm getting negative 1.50 for that one. It's negative 1.49 something. But if you round it correctly to two numbers after the decimal, it's negative 1.50. The other one, 130.5 minus 135 divided by the square root of 13.5. I'm getting negative 1.22. Yeah, okay. And now how do you do a z between problem? It's going to be probability z less than or equal to the number on the right minus probability z less than or equal to the number on the left. And now each of those are less than, so each of them you can look up in the table. So the negative 1.22, let's look that up in the table. Negative 1.22. So negative 1.22. Looks like that answer is 0.1112. To get this number, you have to look up negative 1.50 in the table. Negative 1.50, so negative 1.5, last digit 0. 0.0668. Okay, so you subtract those. And I'm getting 0.0444. Again, that's not the exact answer, that's an approximation. And that's how you do that. Okay, guys, so that's the end of this section.